Okay, the objectives today for our Chapter 4 is to describe the concepts of signature analysis, detect normal suspicious traffic signatures, identify suspicious events, and in a later class we'll explain the common vulnerabilities and exposures, CVE standards. When we talk about signatures, we're actually thinking about factors or attributes of things that set them apart. So when we think about a signature analysis, if we're talking about a handwriting signature, there's experts that can look at handwriting samples and to tell whether someone wrote something or not. Well, we can apply that same concept to looking at network traffic signatures, and we've seen some of the headers and content when we were talking about TCP/IP, and we're able to look at those signatures and tell what type of traffic it is. Now what we're going to do is look at those same some of the same concepts, the TCP/IP packets, and determine whether there's something anomalous, whether there's something wrong with these packets, or whether they're just normal packets that flow freely across the network every day. So, as a definition, the signature is a set of characteristics used to define a type of network activity, and this can be things that typically we consider are good, which is FTP traffic, HTTP traffic, send mail traffic, and so on, or they can be nefarious. They can be things that are done for bad as opposed to good. And sometimes you can see traffic that could be either bad or good, but it needs to be taken into a larger context. For example, sometimes a network administrator may need to determine what systems are running on their or what systems are up and running on their network, as well as what ports are running, because a system administrator may want to know whether somebody is opened up a port that should not be open. And so some of those signatures that are sent out look exactly the same as somebody trying to determine whether any vulnerabilities that are open in terms of network services on computers on a network. Intrusion detection devices. When we say an intrusion, what are we talking about? Typically, we're talking about an outsider trying to break into a computer, and that can be somebody who's outside the network, but can also be an insider that's trying to make an intrusion into a computer that's on the network. So some devices, the network intrusion devices, assemble databases of normal traffic signatures. And then what the intrusion detection device does is it parses this traffic and then compares them to the normal signatures, and if there's anything that looks different, then it signals an alarm. These are called anomaly detectors. There's actually two types of intrusion detection devices. Those that can be put into the anomaly detection category, or those can be put into the signature category. Other devices refer to a database of well-known attack signatures, and so notice that those two types of intrusion detection devices are looking at traffic in different means. One is comparing it to good known traffic, and another is comparing the packets to bad traffic. Now, if we want to just flip over here quickly, hopefully I've got Snort running. Here we go. So this is our Snort database of rules. Snort is an intrusion detection system, and it does a signature analysis. So all of these files are individual files that contain signatures of known bad traffic. So let's look at DDoS rules, LS DDoS rules, and take a look at some of these. So here, and this may not make any sense right now, but it will later on. But this right here is a signature. And essentially what Snort does is that each time a packet comes through, it compares it to each of these signatures to determine whether the packet meets the signature requirements. And so, for example, this says that it wants to send an alert when you have ICMP traffic from anything coming in from the outside to anything coming to the inside network. It wants to send the message DDoS Tribal Flood Network Probe, and the ICMP type is 8, and the content is 1, 2, 3, 4. So Snort knows that there's a high probability if these conditions are met right here, this ICMP traffic coming from any port on the external network to any port on the internal network with an ICMP type of 8 and the content is 1234, then it's probably a DDoS tribal flood network probe. And so essentially, this is a signature, that's a signature, this is a signature, and so on. And so there's quite a few of these as we just scroll on down. And notice that there's lots of different rule sets that the packets can be compared to. Let's jump back over here. One of the problems you have is false positives and false negatives. A false positive means that there's a packet that's compared to some of the rules, and the intrusion detection says, this is a bad rule, so it flags it as bad. Where in actuality, it's just something that's commonplace that is not bad. That's called a false positive. A false negative, on the other hand, is when the packet is let through that the intrusion detection system doesn't flag it as bad when actually it is bad. So these two conditions are bad. The false positive, which intrusion detection systems are prone to, means that it's essentially the same as your fire alarm going off, let's say, 20 times at night. So it keeps on going off, so after a while you go and you turn it off. Well, that's one way that intruders get around intrusion detection systems, is that they start creating a lot of what appears to be false positives, and so that the systems administrator doesn't take as much care in looking at those packets. A false negative, on the other hand, means that somebody who has a nefarious intent is actually slipping through and actually getting by the intrusion detection system. So signature analysis analyzes and understands TCP/IP connections. This actually means the intrusion detection is able to take each packet, break it down into its constituent parts, which is peeling off the various layers of the TCP/IP stack, and then it compares that information to the information in the rules. And the intrusion detection system then can determine whether a packet is legitimate or whether it's suspicious. Bad header information is a common way in which packets are altered. So something in the packet, whether it's a port address, whether it's a source address, and so on, can be altered to try to get around the intrusion detection system. And so suspicious signatures can include malformed source and destination IP addresses, source and destination port numbers, IP options, protocols, and checksums, and IP fragmentation flags, offset, or identification numbers. So if you think about it quickly, what would be an example of a malformed source address? Let's say one coming in from the outside. So you've got a packet coming in from outside your network. What would be an example of a malformed source address? How about, I'm just going to type it here, or anything in that range, or actually anything in this range. Oops. Later on we'll talk about this notation. It's called CIDR notation, classless internet domain routing notation. Essentially what this means is that this is given a network address, and this is given the range of addresses on this network. But what is this address? That is a private network address that you should only see behind a gateway that's running NAT, right? A network that's running NAT. And therefore, anything coming in that has this address has to be malformed, because there's no network that's sitting out, there's no computer sitting out on the internet that has this address. And later on we'll see how that can actually be used to create an attack. Bad header information, for example, the checksum, simple error checking procedure. We saw earlier how there's a 16-bit checksum that's created for various levels, for various level headers, and so that can be malformed as well. And a checksum, I think we've talked about this. A checksum is like we did earlier. The simple example of a checksum is the MD5 sum. MD5 sum is a mathematical algorithm that creates a unique number that's associated with the contents of the file. And so this is essentially a checksum. It's a 128-bit checksum. However, Most checksums are only going to be 16 bits because 128 bits is really overkill for just doing a checksum on a network packet. So 16 bits will work just as well. There's no need for 128 bits. And so a checksum determines whether a message has been damaged or tampered with while in transit. You also have suspicious data payloads, and the payload is actually going to be the data associated with the packet. And as we'll see later on, in fact, what you'll see in your first assignment is that some payloads may contain data that indicates that they've got a suspicious activity, for example, asking for information they shouldn't be asking for, and so on. There are also some known attacks that occur. For example, there's a flaw in the Unix sendmail program that can cause, in fact, there's been quite a few flaws in the Unix sendmail program. That's an SMTP program, Sendmail Transfer Protocol. It's actually used to send email from a computer out to other computers on the internet. And that's been susceptible to a lot of buffer overflows, which we'll talk a little bit about later on. But essentially, what that means is that attacker is able to send a buffer overflow and gain escalated privileges to a computer if they're good enough by sending crafted packets to a program, to a computer, rather. Then you have single packet attacks, known as atomic attacks, and they're completed by sending a single network packet from a client to a host. There does not need to be a connection established, which would mean that if there were a connection established, that would mean it would be using the TCP/IP, the TCP layer protocol, right? Because the connection would require that three-way handshake, and this only requires a single packet. And a good example of atomic packet, which no longer you can do, but it was called a ping of death. And what that occurred was that the under Windows, Windows wouldn't check the size of the data on a ping, and so if you sent a ping that had too much information, it would actually cause Windows to general protection fault, that is to shut down. Then you have multiple packet attacks, also called composite attacks, and so these would require a series of packets to be received and executed for the attack to be completed. And usually most of these will require a three-way handshake, a connection, so that's going to be looked at from the TCP level. And these are difficult to detect, because sometimes, for example, an ICMP flood involves a ping, which uses ICPMP, which are packets that are quite common running over the network to determine whether a computer is running or not. And so it has, it's used by system administrators for non-nefarious purpose, but also it can be used for denial of service attacks. And you might see one of those in your next assignment. You just have to tell me whether it's if you're able to distinguish between an ICMP flood or whether it's just a network administrator determining whether systems are up or not on the network. So how do you capture these packets? Well, we've already looked at how to do that with tcpdump and with Snort. So essentially these are called packet sniffers. And packet sniffers can be either software, which we've seen, or hardware that monitors traffic going into or out of a network device. And the packet sniffer captures information about each TCP/IP packet it detects. And what this allows you to do is either A, study these packets by hand, which is long and tedious and fraught with error if you're just doing this manually by hand, or you can have the intrusion detection system take a look at the packets and compare those against its known signatures to determine whether a packet is reasonable or not. Okay, this is looking at an example of a single ICMP echo request packet capture. And well, let's take a look at that right now. Let me see. Let's capture some of these. First of all, let's look at, I'm running under Linux now, so if I want to see what the network interface is, I can type ifconfig -a, and from your Linux classes, you can see that we have really three interfaces, two of which we're only concerned with. We have ETH0, which is our Ethernet. We see have our internet address. And we have our loopback, which is used for inter-process communications on our computer. Okay, so now if we want to listen, we can type tcpdump -i ETH0, and let's write this out to a file called icmp.pcap. And now what we're going to do is let's go out here and let's ping some other computers that have open up here. And so let's ping 192.168.0.2. Okay, so what's happening here? Let's stop that. Here we're sending out, this computer is pinging 192.168.0.2, so it's sending 64 bytes of data, an ICMP packet, and sending out an echo request, which is ICMP type 8, and it's sending it here. And if ICMP packets are allowed to flow across this network, that is if they're not being filtered, then 192.168.0.2 will actually be sending a response back. And we see that it is sending a response back here. These are the responses. It's sending back 64 bytes of data from this. And notice it's got the sequence number here, the time to live, and the number of milliseconds for the computer to respond. Now let's go over here and take a look at, notice that we've captured 46 packets here. There were 0 dropped. This says 0 dropped by the kernel. If the packets are coming across too fast for the kernel to actually process, then packets will be dropped. So we type tcpdump read pcap, and notice there was quite a bit of activity here. And we're going to search for, and here's what we've got here. If we want to look at so let's go back here and parse this out. This is the ICMP packet, and this indicates the hour, minutes, and seconds in which it was sent, the month and day, the MAC address, source and destination. Remember, the MAC is a media access control address, and it's a unique number that's associated with your network interface card. And of course, it's the way that computers, once you get on a network, actually speak to each other. Routing occurs via the IP address, but once you get on your own network, it's via the MAC address. And so each source IP address will have its own MAC address. So this is associated with this, this is associated with this. It's a protocol ICMP, Internet Control Message Protocol, the time to live we've talked about. See other information, ICMP type and ICMP code. And so this type and code 0 indicates it's an echo request. And then there's no real, this has ASCII payload, and this is just, letters that don't really mean anything, because really what we're doing is we're just asking for an echo request to determine whether a system is up or not. So let's see this in action. I've opened up the Ethereal. I'm going to capture this down. Recall from our TCP dump that we need to identify the network interface card to listen in on. We have our generic dial-up adapter, which I don't have a modem, so it's not going to work. So we want our gigabit Ethernet adapter. We select that, and we can click Start. And then so it's going to be capturing packets. And then let's click Run. And let's ping 192.168.0.2. Great, so we've got some packets. We see that 0.2 replied. So now what we want to do is, oh wait, maybe it's save this in here. There we go. Okay, so what this is saying is I want any ICMP, any packets that are identified as ICMP, we're going to apply to that. There we go. And so we see that the packets 38, 39, 42, 43, 44, and so on down here were ICMP packets. And so notice that the first one here is 192.168.0.7, which would be the IP address of this computer, and we're sending it to this one. How do I know what my IP address is on this computer? Hopefully you all already know how to do this, but let's just run through it. You know, you have ifconfig utility that you use under Linux. We use ipconfig under Windows. And here we go. We get all our Windows IP configuration. And we see that for the Ethernet adapter, the IP is 0.7. So we know we're talking about this computer, sending something to this computer. ICMP echo a ping request. Now let's go down here and look at the details of it. So we can go down to the information down here, version 4, header length 20 bytes. If we look back at our TCP/IP notes, we see that's correct. The total length is 60. Flags is 0. And time to live is 128. Let's go down to the actual data section down here. Notice it says the checksum is correct. Notice that the 8 and 0 that we saw over here in our PowerPoint, that's correct, is type 8, echo request, code 0, the checksum is correct, the identifier, and the data, which is meaningless. Now let's look at a reply. So this is the reply coming back from .2, and all this is the same until we get down to here. Notice this is an echo reply, so this is type, ICMP is type 0, code 0. So an echo reply is type 0, a request is type 8. And it's got pretty much the same gibberish down here, 32 bytes of data. And so we see that there were several requests and responses for ping. Okay. And so now this is a TCP packet capture. Here we have the date and time, source port address, IP address, source address, destination IP, destination address. Let's look at this destination address here, 80. Now if you don't know in this class, if you don't know what some of these are, then there's an easy way to find out. I'm not going to tell you what each of these are, but usually a destination address coming into a network, well-known port numbers. And so we can go down here and find out that 80 is HTTP, the web. Notice this can be TCP or UDP. There's 65,536 ports, and there's 65,535 ports for TCP, and there's 65,535 ports for UDP. The ones that run from 0 to 1023 are the well-known ports, and those are usually restricted to being run by root. And so when a client needs to connect to a server, it will select a port randomly that's above 1023. And so that's why if we go back here, we see that this port is 3927. That was randomly selected by the computer to connect to this. So well-known ports are for services that are commonly exposed to the internet. So 80 would be the port for HTTP, your web. If we go back here, if we want to search for, if you see something that says 21, we can scroll back here. We see that 20 and 21 are going to be for FTP. 21 is for control information, and 20 is for the actual data that's crossing the network. If I said 25, you would go here and you'd see that's SMTP for Simple Mail Transfer Protocol, and so on. If I said, what about 55,555, that should tell you right away that that's not a well-known port, but that's ones that are randomly selected by a client as a client port. And if we go all the way down to the bottom, we'll see that 55,555 is not actually on here. Notice that actually that some of these, because there's only a limited number of well-known reserved ports, that some of the actual upper things that are above 1023 can actually also be used for well-known services as well. So 10,000 used for Network Data Management Protocol. Let me search for 31337. Oop, that's not listed on here. Okay, that's a that's actually a back door, but that's not included on here. I'm surprised. Okay. Okay, let's go back here. Notice now we're talking about protocol is TCP, time to live, IP length. Notice the flags that are set, ACK and push. This is an acknowledgement. It says push. That means don't wait for the rest of the data. Go ahead and capture that data. Don't wait till the TCP window actually fills up. We have a sequence number and an acknowledgement number. Here's the window size. Notice all of these are in what? 0x is what? Hex. And then we have our data area. So if we actually go back and take a look at this one more time, and what we'll do is we'll capture some more packets. Okay, the generic dial-up adapter, we don't want that. We want our Broadcom. Let's start. Now let's download a, back and stop this. Notice that 44 packets have been captured, TCP, 8 UDP. Let's stop. And let's type in here TCP IDENT. Apply. Oop. Okay, we just want to see if TCP flags are present, because they always should be. We're going to apply. There we go. And so here we have, notice that this is this computer connecting to this destination address over TCP. Notice it's going to port, what would this be, HTTP? That would be 80. And we have a synchronize, a SYN, ACK, and an ACK. So this first 3, 4, 5, and 6 is actually a three-way handshake between this computer and this computer. So notice this initiates the connection with a SYN to this computer. This one responds with a SYN ACK. Yes, I want to connect. I acknowledge that. And then finally, the final ACK. And so now there's a three-way handshake between those. And so that three-way handshake occurs at the TCP level. So now you can actually work at the application level, which is HTTP. And so now this computer sends a GET request over HTTP there. And if we look down at this data area, we see that HTTP, this is the actual request that is being made from this computer to that computer. Notice that the source port is 3276. That's from this IP address, my computer, randomly chosen, and the destination is this over HTTP port 80. And there we go. Okay, let's move on down. So what does a Trojan program signature look like? This is just an example of it. Notice that the attack IP is any, so this could be coming from anywhere. Notice that this directional arrow indicates, this of course is the source and the destination, and so this is actually indicating the source over here, the destination over here. And so anytime an attack, a Trojan program, you see the port 317090 as the source, and the destination is this. That indicates that that is a Trojan. Notice down here that's just saying 41, that's hex, and that's hex for a capital A. What are some packet sniffers available? We've talked about some of them. We've talked about Snort, which we'll get into much in depth later on. We've given you examples of Ethereal, as well as tcpdump. And this is just showing using Snort to capture TCP and UDP. Okay, detecting traffic signatures. We need to detect whether traffic is normal or suspicious. And you never know because there's so many of them, so the best thing to do is to utilize intrusion detection systems to tell you whether traffic is normal or suspicious. If you do see something that's suspicious, that doesn't necessarily mean 100% that it is. That just means that Snort has flagged it as something that looks inappropriate. So how do you tell if something is suspicious or not? One is by looking at signatures. The other is actually understanding the type of traffic that travels across your network, which means that requires network baselining. And network baselining is the process of determining what is normal for your network before you can identify anomalies. You should know whether FTP traffic is occurring on your network. You should know whether telnet traffic. You should know what services are being run on the computers within your network. You should know whether there should be outgoing ICMPs or incoming ICMPs. Once you know that, once you know what your network traffic looks like, then you can actually look at traffic that's crossing your network and determine whether something's wrong or not. But in order to do that, it requires a lot of groundwork by doing some network baselining. Okay, normal traffic signatures. These are the possible TCP flags. There's a SYN, notice these are hex numbers. SYN, ACK, push, urgent, reset, and fin. We know that the SYN and the ACK is used always to acknowledge a packet. SYN is used to synchronize a connection, to start a connection. Push is used for a lot of applications to tell the receiving computers to go ahead and process this without waiting for the TCP window to fill up. Urgent is used to indicate that a request is urgent. Reset is used for several reasons. The most important of which is if a computer is trying to connect to a port which is not open, the computer will send a reset packet back. And a fin and ACKs are used to actually close a connection. So you know you have a three-way handshake here. There's actually going to be two three-way handshakes to actually close a connection. So placement and use of these flags are definite. The deviations from normal use mean that the communication is suspicious. And later on we'll see how there's ways of actually trying to do a network scan that involve non-normal use of these packets, such as fin scans or ACK scans, and which would indicate that something is suspicious is going on. To continue using tcpdump or Ethereal to capture packets, look at them, take a look to see what is normal. Go out and ping your own computer. You know how you can do this is by pinging, for example, you can ping 127.0.0.1 and capture some of those packets and take a look at them. You can. This is while you're running tcpdump, and I've already shown you how to do that. Or go out and, if you know there's an FTP server out there, or a telnet server, connect to it, capture some of those packets, and take a look at them to see if you can tell what are the defining characteristics of those packets.